The homework for tonight is to finish the lab, and you should be able to do the calculations for the mixing of the water. And the second part of the lab was the enthalpy of solution part. Now, what we're trying to find is the delta H to dissolve a salt, and we want to find it in either kilojoules per mole or joules per mole. That's typically how it's written. So let's think about a salt. Let's say that we have a salt AB, with A being the cation, like, so say, for example, we were dissolving sodium hydroxide. Well, this is going to break into its ions. And when it does that, it can have an energy change. Most salts do. And it can either give off energy, and if it gives off energy, then we know that the delta H would be negative, exothermic. If it takes in energy, then the delta H will be positive. Now, the system in this lab activity, the system is the reaction. The reaction is happening in the cup. So if we think about the reaction happening inside of this cup of water, the water is the surroundings. So we're going to measure what happens in the surroundings, and since we know that the Q of the system will equal the negative Q of the surroundings, we can figure out the Q of the reaction, the heat of the reaction. I'm going to give you an example. It's going to be completely made up, but this should allow you to do the calculation for all of the class data. You need to do the calculation for every single group's class data for both the sodium acetate and the sodium hydroxide. Unfortunately, not every group did all of them, and so there's actually only 4 or 5. I'll put the table here at the end. Okay, so let's say that we have a compound, AB, and we'll say that we have a molar mass of this compound is 50.0 grams per mole. And we're going to take 10.0 grams of AB, and we're going to dissociate it. We're going to dissolve it in water, and we're going to dissolve it in exactly 100 grams of H2O. And we're going to measure the initial temperature of the H2O to be 22.3 degrees Celsius. So I'm just making some information up to give you an idea of how to calculate this. And at the end of this, we're going to measure that the temperature of the water goes, in this case we'll say goes up to 26.3 degrees Celsius. Alright, so what happens? We take AB, it dissociates in the water to its ions. In the process of doing that, the temperature of the water goes from 22.3 degrees Celsius to 26.3 degrees Celsius. So this is T final and this is T initial of the surroundings. So let's look and see what the heat change was. So the Q of the water is going to equal mass of the water, C of the water, delta T of the water. So I've chosen some nice easy numbers. Yours will be more realistic, not so cookbooky here. So we're going to put in 4.18 joules per gram degree Celsius, and the change in temperature, I picked a nice number, 4.0 degrees Celsius. Okay. This gives us a heat change of 1,672 joules went into the water. Where did that come from? That went into the water because the temperature went up. That has to equal the negative of the system. Right? So I'll go to the next page. Since we know that the energy from one has to go to the other, we write this often where the negative energy of one equals the positive energy of the other, so one goes up and one goes down. So if the water went up 1672 joules, that means that the system, the reaction, was negative 1672 joules. So this is the delta H for the dissolving of the salt, and this was the delta H if we dissolved 10.0 grams of AB. Now typically delta H gets written as kilojoules per mole. So we need to figure out if that many joules dissolved, we would like to know how many kilojoules per mole. Well, we know that Negative 1672 joules is the same as minus 1.672 joules. And now we need to divide by how many moles we had. Well, we had 10 grams of the salt, and we know that 1 mole of the salt is 50 grams, so we had 0.2 moles. So if we put 0.2 moles on the bottom and we divide, we get that the heat of solution for this salt, this pretend one I made up, is negative 8.36 kilojoules per mole. So if I was to dissolve 1 mole of the AB, it would be exothermic and give off 8.36 kilojoules. So a lot of times you'll see that written like this. AB makes A plus B minus plus 8.36 kilojoules. And when you write it like that, that means that this corresponds to 1 mole, because this is a 1 in front of that on the reaction. Sometimes you'll also see it written like this. Delta H equals minus 8.36, and it would be kilojoules per mole. So that's the type of calculation I expect you to do in your lab for all of the class data. You're going to do 1 for every line, and then at the end, after you get the delta H, you're going to average them all. I'll put the table on the next slide. Okay, so you have 3 trials. You're going to calculate the delta T. That's in this first column. That's easy because you're just subtracting your 2 T's. You're going to calculate the delta H, and that's just finding the delta H based on the amount of water and the change in temperature of the water. Okay, so we have just the amount of water, and the change in temperature. So to do the delta H, you just need the change in temperature in the water. And then the last column, this column here, is delta H in kilojoules per mole. So you're going to take this delta H and you're going to divide it by the number of moles that you had of your substance. Okay, so let's see, this was grams of NaOH. We have a new table down here, so I'll break these into 2 tables. Okay, so you have 3 different sets of data for the sodium acetate. You're going to fill in these 3 rows, and then you only have 1 set of data for the sodium hydroxide, and we will talk about the results in class. Just one last thing, just in case you forget, sodium acetate, you should be good at this now. The reaction to separate it into its ions, the dissociation looks like this. Okay, and for the sodium hydroxide, and when you're calculating the molar mass of the sodium acetate, the molar mass of this, be careful because it was a .3H2O. So I'll put when you're calculating the molar mass of the sodium acetate, in order to get how many moles you had from the weight, from the mass in the lab, you need to include that entire molar mass. That's what we used. That's what that salt was. This was a .3H2O. So it's not just the molar mass of this, it's the molar mass of the entire substance. Sodium hydroxide was just plain, it wasn't any hydrate. Okay, and that you only need that for when you're trying to do this last column, because you need to divide it by the number of moles you had, and you won't know the number of moles you had correctly if you don't do a hydrate.